The second model of influence in a crowd, we'll be talking about it, try to model the concept of tipping. And this is the first time that we'll be encountering a positive feedback. But first of all, let's look at the basic model here. Okay, should I buy, say, an iPad? And let's model that this decision you're going to make will depend on how many other people out there have already bought an iPad. So there's a dependence on the global percentage of adoption at the current time t. And if everyone thinks like this, then we can model an evolution from time t to t plus 1 in discrete time jumps of the percentage of global population at time t plus 1 adopting, say, iPad as a function of the percentage of people adopting iPad at time t. This basically is a macroscopic view of the microscopic individual decision. And then in the next lecture, we'll be looking at local instead of global percentage of adoption, where topology of the underlying graph will play an important role here. So as a static analysis, we can see this as a positive externality. The more people adopt a certain product service, the more people will adopt it in the next iteration, which could be the next week, next month, and so on. So if we just look at one iteration from t to t plus 1, we can see a positive externality. In contrast to the negative externality that we have seen, for example, in power control in chapter 1, in auction in chapter 2, and in voting theory in chapter 6. But as we look at the continuous evolution from one time to the next, to the next, to the next, look at this entire dynamic system, we also feel the positive feedback. Because the more people use it, then the next time there will be even more people use it. And this keeps on going. This positive feedback happens all the time, ranging from a microphone during tune-up, giving you a very sharp squeeze, to unemployment rate staying high as the unemployment benefits continue. All those are examples of positive feedback. We'll later also look at negative feedback examples in the dynamic system, especially in chapter 14 for TCP congestion control on the internet. So now we're going to make it a little bit more precise and then visualize this trajectory of the dynamics. We'll say that there is a certain percentage of adoption in the global population, P, over discrete time slots indexed by T. And this influence function that captures the aggregate of the individual decision as a function of current global percentage of adoption is represented by a function f of p. So the shape of this function f of p will determine a lot of things, including the existence, number, and the properties of equilibrium. Here is a typical way we visualize the trajectory. We plot this f of p as a function of p, and the trajectory over discrete time slots t will be viewed as an arrowed line. This solid line is the actual function shape f of p. As you can see, this is a function that is concave first and then convex. The dotted line here is just the 45-degree angle line from the origin. It would be useful as a tool for us to visualize the dynamics. So now we would like to plot one iteration, that is f of p at time t gives you p at next time t plus 1. So first we have to look at this p and stick it into this function f, and that can be done by basically going above from the current p to intersect at the function f. So going vertically up to hit the line is basically visualizing this operation. And this equality here is then visualized by going horizontal to the next level. Okay, this basically says next time when you look at P, please start from this value. Because it stops at this 45 degree angle line, that means next T will be exactly the same value as this one. So one vertical is this functional evaluation, one equality is this the horizontal line. So one zigzag represents one iteration, and then you can keep zigzagging, or if you start from here, then you zigzag downstairs. As you can see, the shape of this curve and where it intersects the 45 degree line makes a big difference. Okay. First of all, where it intersects the 45 degree line is so-called equilibrium. Why? Because if I start with this P at time 100, then at time 101, where would I be? I would still be at the exact same value. I don't have to go vertically. I am already on the curve. This is where the curve strikes 45 degree line, and I don't have to therefore go horizontal either. I will stay at this spot forever unless there is some perturbation around it. So we call this an equilibrium. Now let's look at a different shape of f of p. Still, this one cuts across 45 degree line only once, but it is convex first and then concave. So there is an equilibrium, and this is the unique equilibrium. But as you can see, if I start at equilibrium but perturb it ever so slightly, then I start following this vertical, horizontal zigzag. I'll be going down this way all the way to the other equilibria. Actually, there are 3 equilibria. In this case, this one is the only non-trivial one, and then at the boundary condition of 0% adoption, 100%, there are 2 other equilibria. Okay. So if I perturb it ever so slightly downward, I'll end up all the way down to the other equilibrium at 0. Whereas if I perturb it ever so slightly upward, then I'll end up being the 100% adoption equilibrium. So I can see that this influence function f of p intersecting with the 45 degree line, that those points are equilibria. Some are stable equilibria, because if you start from some points away from it, you're going to eventually converge to that point. Some are unstable equilibria, because once you have a slight perturbation around it, up or down, you will move away from this equilibrium towards another equilibrium. And in general, for influence function f of p that cuts across 45 degree line only once, if it is concave before and convex after, then that equilibrium is stable. On the other hand, if it's convex before, concave afterward, like a sigmoidal function, then that is an unstable equilibrium. And this equilibrium and concept of stability is associated with basically a fixed point of an iterative procedure, not associated with the Nash equilibria of a strategic game. So here's a simple example. Now, what we really want to do is actually be able to estimate the reaction of the population, draw this curve, and then find out where are the stable and unstable equilibria. If you want your service or product or your music to be adopted by 100%, for example, then you want to move away from an undesirable equilibrium. If it is unstable, you want to perturb it upward and move towards that equilibrium. This is what we call the attraction region. So once you can perturb P a little bit away from this unstable equilibrium, you can push it all the way to 100%. It triggers a chain reaction towards what you want. But the challenge is, how do you estimate the curve, and how do you raise a campaign to push people away from those equilibria? Those are where the gaps exist between theory and practice. But we can look at a very simple numerical example here. You see 2 influence functions, f1 of p and f2 of p. f1, the dotted line, turns out to be this sigmoidal function 1 over 1 plus e to the power minus 12 p minus half. And the solid line is another influence function of the shape half plus 1 over 12 log of p over 1 minus p. Actually, the algebraic expression behind these 2 curves don't really matter. We just design them so as to illustrate our point. These two curves, they each have the following three equilibria. The one is clearly this one, which is half. Okay, 50% adoption is an equilibrium. Whether it's stable or unstable depends on the shape of the curve around it. There is also another equilibrium here, okay, which is almost zero, 0.00255, and another over here, which is almost 1, 0.9975. That's 99% adoption. This is less than 1% adoption, 0.2%. And we designed a curve such that if you perturb around it a little bit, it's going to show different behavior. For the first one, f1 of p, you see that the equilibria at the two extreme points are stable. Okay? This equilibrium is an unstable equilibrium. And indeed, if I perturb it a little bit downward, okay, to, let's say, instead of 0.5, I say it is 0.5 minus 0.001. And that little perturbation will trigger a trajectory along this curve, bouncing all the way, this is the 45-degree line, all the way eventually to the other equilibrium, which is almost 0%. Whereas for the second kind of influence curve, if we perturb, for example, from here, the near zero adoption equilibrium, 0.2%, by perturbing it 10 to the minus 5, then within about also 10 steps, it will actually climb up all the way to the 50% adoption equilibrium. So for the dotted line F1, this is unstable equilibrium, a little perturbation brings it down there. And for the second curve, this is a stable equilibrium, and this is an unstable equilibrium, and a little perturbation would move it over here. Now, in the advanced material part of this lecture, we also will introduce two more influence models in the crowd, in synchronization model and a diffusion model in the market. But up to this point, we've already seen two influence models in the crowd, including the information cascade model that try to model the dependence of one's action on peers' actions. And we see the sharp contrast between this and the wisdom of crowd on Amazon simple averaging. The second model is tipping behavior by looking at the shapes of influence function capturing the global population's adoptions percentage impact over a dynamic system. In the next lecture, we'll take these two and then bring it to two more models where topology of the graph will also play an important role.